So let's continue our discussion of how we're going to figure out the mean electric axis of the heart. Let's take a look at this diagram over here first. Here I drew a triangle that is a configuration of 3 leads, and that is the classic Einthoven's triangle. So Einthoven's triangle, a configuration of 3 leads, where lead 1 is up here, and that will be from right arm to left arm, where this is the plus direction, and this here is the minus direction right here. So lead 1 in this direction is positive, lead 1 in this direction is negative. Anyway, so lead 1 is taking a look at the heart, at the electrical activity of the heart from the right arm to left arm perspective. Now lead 2 would be taking a perspective of the heart from right arm to left leg. So down to here is this direction right here. And as you can see, I drew a little heart in red, and in the center right here, you can see that the interventricular septum is kind of pointing down and then slightly to the left. And so from an anatomical perspective, of course. So you can see that it's most closely aligned here with lead 2 EKGs. And that's the reason why the lead 2 EKG is the one that most closely resembles what we picture as an EKG, like the tracing that you have up here. So this lead 2 EKG, that would be something that you would record from lead 2, because lead 2 most closely aligns with the direction of the interventricular septum, which is the mass of electric activity through the heart. Now the last lead here is lead 3. That one will be the perspective of the heart electric activity through the heart going from left arm to right leg. And for most people, the heart sits in their chest cavity, pointing down slightly to the left, but it could be pointing fully down. Then lead 2 and 3 would be equally good. It could be pointing all the way in this direction here, over to the left. So that would be then making lead 1 the perfect perspective to look at the electric activity through the heart. Anyway, so this is just to explain the original 3 leads that make up an EKG tracing. That's known as Einthoven's triangle. Nowadays, of course, they're adding also the 3 augmented leads and then the 6 chest leads, and so that makes it for 12 lead EKG for a perfectly well-rounded picture of your electric activity through the heart. So anyway, I would like you to know Einthoven's triangle, a configuration of 3 leads, and I would like you to know Einthoven's law. I know it's not in here, but I want you to know it anyway. Einthoven's law states that lead 1 plus, and this is supposed to be a plus right here, doesn't want to write, but here. Lead 1 plus lead 3 equals lead 2. Slightly crooked on a 2, but that's what it means. Lead 1 plus lead 3 equals lead 2. So if you were to add up the electric activity from lead 1 and from lead 3, you would get lead 2. Okay. Now, the way you're going to calculate the mean electric axis of the heart is by adding mathematical vectors, basically. And I'll show you how that's done. So basically, you would measure out the lead 1 vector and put that on the horizontal line right here through the circle. And again, if it's in the positive direction, means it's mostly upward, then we're going in this direction on this circle right here. And then you also take a look at the lead 3 main voltage of electric activity going through as measured with the main EKG complex. And so then you're going to put another vector into your lead 3. So let me just label this in different colors. So here it is. I labeled lead 1 direction, which is exactly horizontal. Lead 2, the direction right here that aligns here with this direction, of course. So that would be this same direction right here. And then lead 3 is this direction right here. And that will be in this direction. So what you need to do in order to calculate the mean electric axis of the heart is measure out how tall is my R wave, basically from baseline, for lead 3 and lead 1. And if they're both positive, then they would be going down here and in this direction for lead 1 and then lead 3. And you just have to measure out how strong the lead is, basically, in either one of those directions. The way you would calculate then the mean electric axis of the heart is by taking a perpendicular. So first you have to put in your diagram how strong was the electric activity. If it's in a positive, it would be going in this direction on lead 1, and then you have to cast a perpendicular. So let me just kind of dot that line right here. So perpendicular would be a 90-degree angle to this lead 1, and for lead 3 you have to do the same thing. You're going to have to cast a perpendicular to lead 3. It's going to be slightly crooked, but anyway, and then they will meet up. The perpendiculars, they will cross at some point, and that would be your mean electric axis of the heart. And in a normal heart, that follows approximately 60-degree line of lead 2, because the normal perfectly sitting in your chest cavity type of heart follows pretty much the lead 2 pattern in this direction. So that would be here your lead 2. And so if you are putting in your diagram the strength of lead 3 and the strength of lead 1 and cast perpendiculars, and where the perpendiculars intercept, that should be your mean electric axis of the heart. And in a normal heart, it's right around about 60 degrees on the circle. If this here is 0, then perfectly going down will be 90, across will be 180, up here will be 270, and so the normal average mean electric axis of the human heart is at about 60 degrees on a circle that starts here horizontally at 0. If you have a left axis deviation, that means that your mean electric axis is outside of bounds and maybe slightly above the 0 right here. So it could be pointing in this direction. That would be above the 0 in this direction here, and that would be a left axis deviation. That is typically due to right ventricular hypertrophy, and we can talk about that some more when we take a look at the questions in the back. A right axis deviation means that we are going too far past the perpendicular down here, so straight down, and we're going too far in this direction right here, and that can be due to left ventricular hypertrophy. So typically one side or the other is getting too large and it's pushing the other side over, and then you have an axis deviation. So that would be left and right axis deviation. And the last two terms are the Harvard step test and the recovery times. The Harvard step test is a test. It's not a very stringent test, but it's basically a measure of your physical fitness. You're supposed to be stepping, doing exercise basically for 5 minutes, and you're supposed to get your heart rate up. And you can do the step test, would be classic. Either you're going to run up and down the stairs, or you can take a step stool and climb up and down for 5 minutes. That should get your heart rate up and get you sweating a little bit. And then the recovery time is how long it will take you to come back to a resting heart rate. So if you're returning to a resting heart rate very quickly after exercise, that means you're in pretty good shape. But if you're still gasping for air 5 minutes after you stop exercising, that means that you probably are a couch potato, and you should start working on that and get better and work on your physical fitness. But the Harvard step test is a not very stringent test of fitness, and it measures how long it takes you to come back to a resting heart rate. Now let's take a look at what you were supposed to do in this lab if we had a physical lab and you could actually do it. So here you have some more instructions. Here's your conduction system through the heart, and then some more descriptions about the components of the ECG. I do like this particular diagram right here. I think that's very good. It spells exactly out what component of the ECG means what. Here will be the P wave duration. Here is the PQ segment, a stretch of baseline, then the QRS complex. Here you have the QT interval. So that will be the QRS plus the segment right here, ST segment, and then another DT wave together. The ST segment is just a stretch of baseline. Remember, segment means stretch of baseline, versus the interval means it also includes a wave. So the QT interval is actually an important measure There's something called the long QT syndrome that leads to cardiorhythmias and some other problems. So here, again, this you should use this as a reference chart. This explains what you were supposed to measure once you have your own EKG tracing. Here are the normal durations of these various EKG components. So that's sort of a guideline for you. Also here, a guideline would be the amplitude of what you're supposed to measure. The QRS complex, the amplitude on a lead 2 EKG, that would be right around a millivolt or so, plus minus a couple. And then here, some more definitions of tachycardia, bradycardia, AV blocks. So you can take a look at that, use it for your reference. Here is Einthoven's triangle explained, with the lead 1 going across right arm, left arm, then the lead 2 going from right arm to left leg, and the lead 3 going from left arm to left leg. So this is basically sort of the tip here of your triangle, and then the heart showing that the direction of your interventricular septum lines up pretty much perfectly with lead 2. Now that's sort of the perfect textbook person, and the heart sits in their chest cavity perfectly normal, average. So some people's hearts point down and some people's hearts point in this direction. So mostly, sort of shifted up. So all of that is still normal. What's not normal is if you have an axis deviation, it goes past the 0 right here, or it goes way past vertical down. So it's going past in this direction. That would be considered an axis deviation. And again, you should know what defines Einthoven's law mathematically. So that's something I usually ask on quizzes and stuff, hint. And okay, so here starts the data report, and so now you're supposed to record P wave, R wave, T wave, the amplitudes. We can make some stuff up. The P wave amplitude isn't awfully important. The R wave, the amplitude we said was supposed to be around on a lead 2 EKG. It should be right around about 0.8 to 1.2 millivolts. And then T wave amplitude is also not that important. The R to R interval, that gives you your beats per minute. So let's say your beats per minute, they said that the R to R interval, let's say the duration from R to R, let's say it was 0.821 milliseconds it is. So 0.821 seconds. So now how do you calculate the resting heart rate from something like that? Well, you would have to go 60 divided by 0.821. That's the measurement from R to R, so from peak to next peak of your QRS complex. So basically you will record P wave, QRS, and then we have a T wave, and then you go into the next P, QRS, and then you can't see it anymore. So you measure the time from here to here, R to R, and let's say we're measuring 0.821 seconds. Now, what's the heart rate? Well, you have to take 60 divided by 0.821. And that turned out to be 73 beats per minute. So you should always round to the nearest full beat. The decimal places don't really make sense in that case. So let's fill out this table with some numbers that make sense. I'm just going to take them from the guideline table and just fill in some numbers that actually make sense. So here I give you some fake data that makes sense, and I'll just put this together just to point a couple of things out. The QRS complex is supposed to be less than 0.12, so I put it here at 0.1. Another thing, a diagnostic number is the QT interval and the ST segment. So the QT interval is ventricular systole. I put it here at 0.4 seconds, and logically, let's say our cardiac cycle time was 1 second, so there would be a heart rate of 60 beats per minute. Then the 0.4 of the ventricular systole plus the 0.6 of the ventricular diastole would be adding up to the full segment. second. Now, some of these measurements are pretty much given, such as the QRS complex and some other measurements. They're pretty fixed, versus the ventricular diastole, for example, that can change vastly with exercise.